Hope you could solve this problem yourself. If you could not, then let's see how this is solved. So we have, for the production of ammonia, 1000 kg of air is supplied and nitrogen from air is made to react with hydrogen, which is 50 kg available. Find the molar composition of the exit gas mixture. Assume air contains only nitrogen 77% and oxygen 23%. And this composition is given by weight. So let's draw the block diagram for this problem. So we have the reactor. Okay. So we have hydrogen, that is 50 kg. Okay, 50 kg, and air is supplied. That means we have nitrogen, that is 1000 kg of air, so 770 kg. Right, 1000 kg of air, so 770 kg of nitrogen, and oxygen, that is 230 kg. All right, so this is my condition. So, and over here in the products, I'll of course get ammonia. I'll get nitrogen, hydrogen, and oxygen. All right. So these products I'll get. All right. So first of all, let's find out the molecular, the number of moles of each, because then only we will be able to go for the stoichiometry. So the number of moles of hydrogen are 50 by 2, that is 25 kilomole. All right. Number of moles of nitrogen are going to be 770 by 28. All right. So that is 27.5 kilomole. And number of moles of oxygen are going to be 230 upon 32. That is going to be equal to 7.1875 kilomole. All right. So once we've got this, then we'll go on for the stoichiometry. So we know that nitrogen and hydrogen react to form ammonia. And if we balance this equation, then this is what we are going to get. All right. So first of all, let's see what is the condition. So we have nitrogen that has been supplied as 27.5 kilomole and hydrogen has been supplied as 25 kilomole. So if we go on for the theoretical ratio, theoretical nitrogen by hydrogen ratio, then that is going to be 1 by 3, right? And when we see for the supplied ratio, the supplied ratio is going to be 27.5 upon 25, which is definitely greater than the theoretical ratio, right? This is greater than the theoretical ratio. Now this, since it is greater than the theoretical ratio, it implies that the denominator is limiting. That means hydrogen is limiting. All right, hydrogen is limiting. Since hydrogen is the limiting reagent in this case, therefore it will get exhausted. All right, hydrogen is exhausted. Since hydrogen is exhausted, hydrogen would be 0. Right, hydrogen would be 0. I guess that's what they have done. Right, so hydrogen is going to be 0. All right, 0 kilometers. Now hydrogen out is 0, so we are going to do hydrogen balance. So when we do that, so we are going to get hydrogen in minus hydrogen out is equal to hydrogen reacted, right? So hydrogen reacted is equal to 25 minus 0, that is 25 kilomoles. Now by stoichiometry, if 1 mole of nitrogen reacts, 3 moles of hydrogen react. Therefore, nitrogen reacted is going to be 1/3 of hydrogen that has reacted. That is 1/3 of 25, right? So that would be 8.333 kilomoles. All right. Therefore, now when we do nitrogen balance, So we'll get nitrogen in minus nitrogen out is equal to nitrogen reacted or nitrogen consumed. All right. So this is going to be, so this would give you nitrogen out as nitrogen in, that is 27.5, minus nitrogen that has reacted, that is 8.333, right? 8.333. Hence, you are going to get this as 19.167 kilo. All right, 19.167. So nitrogen is 19.167 kilomole. All right. Then oxygen, of course, there is nothing with respect to oxygen in the reaction. So oxygen is not going to change at all. So 7.1875 kilomole as it is. Oxygen is not going to change. Okay. And about ammonia, as many moles of nitrogen are going to react, twice the number of moles of ammonia are going to be formed. So ammonia produced is equal to 2 times the amount of nitrogen that has reacted. So nitrogen reacted is 8.333. So 2 into 8.333. So that is 16.67. All right, 16.67 approximately. Right, so this is 16.67. So we have got this complete block diagram. Now we need to find the molar composition. So that is going to be component, then moles and mole percent. So the components include ammonia, then unreacted nitrogen, hydrogen, and oxygen. Right. So ammonia is how much? 16.67 kilomole. Nitrogen is 19.167 kilomole. Hydrogen is of course 0. And oxygen is 7.1875 as it is. So you'll get 43.0245 as the total number of moles. So mole percent is individual upon total into 100. So that is going to be 38.745%. Then for this you'll get 44.55%. This is going to be 0, of course. And this is going to be 16.705%, right? So when you add, this should be 100%, right? So that's what is asked over here. I have asked you to find molar composition of the gaseous mixture. So that's the molar composition, all right? Hope you are clear with this problem. So once you're done with this, next we'll come to some other concept. So this is similar to, this is related to this particular part only. So if you have a particular reaction in which A is the limiting reagent and B is the excess reactant, right? So in that case, the percentage excess of B is going to be moles of B that are supplied minus moles of B that are theoretically required upon moles of B theoretically required. All right. So this is one very important formula for percentage excess of B. All right. And then percentage conversion. From here, we get another very important term, that is conversion. This is quite a lot used. So please keep this in mind. Percentage conversion is basically moles of A supplied minus moles of A remaining upon moles of A supplied. All right, into 100. Okay. So usually this, if reaction proceeds to completion, then A is your limiting reactant, right? A is your limiting reactant. So if it proceeds till completion, then this becomes 0. So in that case, the percentage conversion is going to be 100%. All right. But if the reaction does not proceed till completion, then we are going to calculate the percentage conversion depending on whatever the moles of A are remaining. All right. So with this, we go on to example number 4. This is quite simple. So first of all, just pause the video and draw the block diagram and do whatever solving you can about this question. That is, you need to find the limiting reactant. You're supposed to calculate that what will happen if all of the limiting reactant gets consumed. And then we'll come to percentage excess and percentage conversion that you can stop while I make you do that. All right. So please pause the video and try to solve this particular part yourself. So hope you all try to solve this problem. Let's see how it is done. So first of all, we are going to draw a block diagram. So this is my reactor. Here I'll feed sulfur dioxide, then oxygen, and over here I'll get okay. So oxygen supplied is 2 moles and sulfur dioxide supplied are 10 moles. So it's 2 moles and here it is 10 moles. So let's see. Theoretical, first of all, the stoichiometry. So stoichiometry gives you this. So theoretically, if you see, SO2 upon O2 is going to be 2 by 1, right? And supplied, if you see supplied, then SO2 by O2 is 5, that is 10 by 2. That is 5, right? So that means that definitely oxygen is limiting, right? Oxygen is limiting. And they have allowed the reaction to proceed, right? So there has nowhere been mentioned that it has been stopped somewhere or something like that. So reaction is completing. So oxygen is going to be 0 kilograms. All right. Oxygen is going to be 0 kilograms. All right. So from here, when we do oxygen balance, so oxygen balance gives us oxygen in minus oxygen out is equal to oxygen reacted or oxygen consumed. So oxygen reacted is going to be equal to 2 moles, right? It's going to be 2 moles. Then by stoichiometry, we know that sulfur dioxide reacted is twice of what oxygen has done. So it's going to be 4 moles, right? So now when we form SO2 balance, so we'll get SO2 in minus SO2 out is equal to SO2 reacted, right? So SO2 reacted is 4, SO2 in is 10. So you'll get SO2 out as 6 moles, right? So SO2 out, you will get as 6 moles. So SO3 from here, when we go on to find out SO3, so SO3 prepared is same as SO2 reacted by stoichiometry, right? So that is equal to 4 moles. So SO3 is going to be 4 moles. All right. So hence we have got SO3 prepared. All right. Then they are asking you percentage excess. Hopefully people could have done, could do till here, right? So now we go on. So percentage excess we needed to calculate. So percentage excess is basically, we saw the formula, moles of B, that is the excess reactant, SO2. The moles of SO2 supplied minus SO2 theoretically required. So first of all, let's see what is SO2 theoretically required. So SO2 theoretically required is equal to SO2 by O2 theoretical, the theoretical ratio, into O2 supplied, right? That is theoretically required. So SO2 by O2 theoretical is 2 and the amount of oxygen supplied is again 2 moles, right? So that is going to be 4 moles. That you can obviously see that over here, if 2 moles of oxygen are supplied, then definitely in stoichiometric proportion, SO2 supplied which should be 4 moles. So 4 mole is the theoretical requirement. So supplied SO2 is 10, theoretical SO2 is 4 upon 4 into 100, right? So this is going to be 6 by 4, right? 6 by 4 into 100, right? So that is equal to 150%. So percentage excess is 150%. All right. Hope you could get that. Then percentage conversion is basically moles of limiting reagent supplied minus moles of limiting reagent remaining upon moles of limiting reagent supplied. So that is 100%. So this is what I was telling, that if the reaction is allowed to proceed till completion, then percentage conversion goes on till 100%. All right. So this is how we calculate these terminologies. This is another question. Go ahead, pause the video and try to solve this problem yourself. Hope you could solve this problem yourself. If you could not, then let's see how this problem is done. Sulfur dioxide reacts with oxygen to form sulfur trioxide. If 100 kilomole of sulfur dioxide was supplied and oxygen was taken from 1000 kilomole of air, calculate the composition of exit gas stream if the exit gas stream contains 180 kilomoles of oxygen, and also calculate the percentage conversion and the percentage excess. So let's first of all go ahead and draw the block diagram for the same. So we have SO2, we'll have oxygen from the air, we'll also have nitrogen from the air, right? Over here, what we'll get would be SO3, SO3, SO2, oxygen, and nitrogen. All right. So there is 1000 kilomole of air supplied, so there would be 210 kilomoles of oxygen, and nitrogen would be 790 kilomole, right? And SO2 supplied is 100 kilomole, right? So this is 100 kilomole. Then we know that nitrogen is not involved in any of the chemical reactions. The reaction that is taking place is this. This is the chemical reaction that is taking place. So therefore, you are going to have nitrogen as it is 790 kilo. Then they have also said that the exit gas stream, it contains 180 kilomoles of oxygen, right? So that means over here we'll get 180 kilomole. All right. First of all, using the supply information, whatever has been supplied, let's see what's the limiting reagent. The theoretical is 2:1 for SO2 by oxygen, right? And supply ratio is 100 by 210. So therefore, this is less than theoretical, implies SO2. Numerator is limited. All right, numerator is limited. Now, but since we don't know whether the reaction has proceeded till completion, so we cannot say SO2 directly equal to 0. So we know exit stream of oxygen and inlet stream information of oxygen. Therefore, we are first going to do oxygen balance. So when we do that, we'll get oxygen in minus oxygen out is equal to oxygen consumed or oxygen reacted. So oxygen in is 210 and oxygen out is 180. Therefore, this is 30 kilomole. Right. Now, this implies SO2 consumed is going to be 2 times 30, right? Because for 1 mole of oxygen, 2 moles of SO2 react. So 30 kilomoles of oxygen means 2 into 30 kilomoles of SO2 would be reacting. So that would be 60 kilomoles. So if 60 kilomoles of SO2 have reacted, then that means SO2 left. SO2 left, or you can say SO2 out, is going to be SO2 in minus SO2 consumed, right? So 100 minus 60, that is 40. And this would be Yeah. So 40 kilomole of SO2. All right, that information we have. Then again, by stoichiometry, we can say that SO3 is equal to SO3 produced is equal to SO3 reacted. Sorry, is equal to SO2 consumed or SO2 reacted. And SO2 consumed is 60 kilomole. So SO3 is nothing but 60 kilomole. So let's go ahead with the composition, right? So components, you have SO3, you have SO2, you have oxygen, and you have nitrogen. If you see the moles, then there are 60 kilomoles of SO3, then there are 40, I think, yeah, 40 kilomoles of SO2, and there are 180 kilomoles of oxygen, and there are 790 kilomoles of nitrogen. So when you add all of them, you get 1070 kilomoles of the total gas mixture. Mole percent is individual upon total into 100. So that is going to be, this would be 5.607%. Then this is going to be 3.738%. Then this is going to be 180.070. So that's going to be 16.822%. And finally, you are going to get 73.833%. So when you add, this will be 100, right? Molecular weight of each. So SO3 is 80, SO2 is 64, oxygen is 32, and nitrogen is 28. So now you're going to multiply moles with molecular weight. So this is going to be 4800, right? And this is going to be 2560 kg. Then this is 5760. Then this is 22120. Total weight you'll get as 35240. All right, 35240. That is going to be the total weight. All right, total weight of the gaseous mixture is going to be 35240. Now this is again in accordance to the law of conservation of mass. See, I tell you. I think example number 2 we did for the same, right? So in example number 2, if you see the total weight, we had the same example, all were the same, just we had not given the exit composition, right? Exit composition was different. But again, the law of conservation of mass states that at any point, the overall mass is going to be conserved. So as you can see, at this particular point of time, when the composition of the exit was different, but still the total mass of the exit was same as 35240. And then you can see that over here as well, in this example, that the total mass is same, 35240, right? So that is what you have. All right. So now, when you find weight percent, that is weight upon total weight into 100. So that is going to be equal to 4800 upon 35240 into 100. So that is 13.621%. Right? Then this is going to be 7.264%. Then this is going to be 16.345%. This is 62.77%. When you add them all, you get 100%. Right? So that is the weight percent or the composition in the molar and weight composition of the exit gas mixture. Now, they have also asked us to calculate the percentage conversion and percentage excess. So percentage conversion, in order to calculate percentage conversion, we have moles, we have the limiting reagent is SO2. So SO2 supplied minus SO2 reacted upon SO2 supplied. So SO2 supplied is 100 kilomole. So 100 kilomole, 100 minus SO2 reacted. Now if you see SO2 that has reacted is SO2 consumed, that's 60. So minus 60 upon SO2 that has been supplied is 100, right? SO2 consumed is 60 and SO2 supplied is 100. So 100 minus 60. Oh, wait, this is not SO2 reactive. This should be, wait, in the formula it was SO2 remaining, yeah. So it's SO2 remaining, not SO2 reacted. SO2 remaining. So this is going to be 40. SO2 out is 40. So this is SO2 out, that is SO2 remaining. So that is 40. So this is equal to 60%. The conversion is 60%. And then you have percentage excess of oxygen, of course, right? Because oxygen is the excess reactant. So oxygen is basically oxygen supplied minus oxygen theoretically required upon oxygen theoretically required in one, right? So if you see oxygen that is theoretically required for 100 kilomoles of SO2 is going to be 50 kilomoles, right? 2:1 ratio should be, so it should be 50 kilomoles, right? So oxygen supplied is 210, but oxygen theoretically required is 50 upon 15 to 100. So this is going to be 320%, right? This is going to be 320%, right? So that's your percentage excess of oxygen. All right. Remember, percentage excess, it might be greater than 100. Okay, that is not a problem. But percentage conversion should not be greater than 100. Percentage conversion is always less than 100. Okay, less than or equal to 100. All right. So that you have to keep in mind. Okay. Now we come on to example number 6. Go ahead, pause the video and try to solve this problem yourself. For the production of ammonia, 1000 kg of air is supplied and nitrogen from air is made to react with hydrogen, which is 50 kg available as the previous question. Find the molar composition of the exit gas mixture given that there is 6 kg of hydrogen in the exit gas. So let's see. First of all, we will draw the block diagram. So this, right? Then we have nitrogen. Nitrogen supplied is obviously 790. No, sorry, it's 1000 kg of air, so 770 kg, right? Because in air, 77% of nitrogen is present by weight. And then hydrogen is 50 kg. All right, hydrogen is 50 kg, and oxygen supplied would definitely be 230 kg. All right, this oxygen will come out as it is 230 kg, and nitrogen, we don't know. Hydrogen, it is given to be 6 kg, right? And finally, you have the ammonia that is going to be produced, right? So first of all, we are going to see hydrogen consumed. All right, since hydrogen we know in the inlet and the outlet stream, so hydrogen balance. All right, so let's make the hydrogen balance equation. Okay, so hydrogen balance gives us 50 minus 6 is hydrogen consumed. Hydrogen in minus hydrogen out is hydrogen consumed. So that is equal to 44 kg, which is 44 by 2, that is 22 kilomole. So these many kilomoles of hydrogen have been consumed. All right. Now we are going to see the stoichiometry. So stoichiometry states N2 plus 3H2 gives 2 NH3. So 1/3 of whatever hydrogen has been consumed, 1/3 of that would be the nitrogen that will be consumed. So that is nitrogen consumed is going to be 7.33 kilomole. All right, 7.333 kilomole, because 22 by 3, those many kilomoles of nitrogen is going to be formed. All right. Those many kilomoles of nitrogen is going to be consumed. So that means when we multiply this by the molecular weight, what I'm doing over here, instead of directly taking everything by stoichiometry, I'm going with the mass basis. All right. So if we multiply this by molecular weight of nitrogen, that is 28, so I'll get 205.333 kg of nitrogen. This much kg of nitrogen has been consumed. So nitrogen left or nitrogen out, if you do nitrogen balance, that is nitrogen in minus nitrogen consumed. So nitrogen in is 770 kg, nitrogen out is 205.333 kg, right? So that is going to give you 564.667 kg. So 564.667 kg of nitrogen is coming out. All right. Now what you can do is you can use law of conservation of mass. All right. Now you can use the law of conservation of mass. So 770 plus 230 plus 50, that is 1050 kg is the inlet, right? And 230 plus 564.667 plus 6 plus, let's call it x, right? So 564.667 plus 230 plus 6, right? That gives you 800.667 plus x, right? This is the outlet, right? So from here, when you solve this particular problem, you will get x as 249.333 kg, right? That is ammonia. 249.333 kg. All right, this we have done by the law of conservation of mass. Let's not do it by law of conservation of mass. Let's do it by the previous method, the way we were doing these problems. So let's just take the similar way. So we'll take nitrogen. So nitrogen is 770 by 28, right? 28, that is 27.5 kilomoles of nitrogen. All right. Then oxygen is 230 by 32, right? So that is 7.1875. So oxygen is here. 7.1875 kilomole of oxygen. And then over here you had hydrogen, which was 50 kg, which means 25 kilomole, right? That was there. Then in the outlet, you would get ammonia, nitrogen, oxygen, and hydrogen. So hydrogen, they have said that is 6 kg, that means 6 by 2, 3 kilomoles, right? So hydrogen consumed is 22 kilomoles. All right, hydrogen consumed is 22 kilomoles. So nitrogen consumed is going to be 7.333 kilomoles, right? So if nitrogen consumed is 7.333 kilomoles, so 27.5 minus 7.333 kilomoles, right? That is going to be 20.167 kilomoles. All right, 20.167 kilomoles. That is going to be left, right? Nitrogen out. This is by nitrogen balance, of course. All right. So this is how we get nitrogen in minus nitrogen consumed is equal to, sorry, nitrogen in minus nitrogen out as nitrogen consumed, right? So nitrogen out is basically 27.5 minus 7.333. That is 20.167 kilomoles. All right. So that's there. And oxygen is going to be as it is 7.1875 kilomoles. All right. Now by stoichiometry that I have written before. So 2 times what nitrogen has been reacted, 2 times of that would be formed. So 2 times of that is ammonia. So 7.33 kilomoles of nitrogen has reacted. So ammonia formed is 2 times of this. So 2 into 7.333, right? So that is going to be, right? So that is going to be 14.667 kilomoles. Right? 14.667 kilomoles. All right. So when you multiply this by the molecular weight of ammonia, right? When you multiply this by the molecular weight of ammonia, so 14.667 into molecular weight is 14 plus 3, 17. Right. So this is going to be 249.322 kg. So approximately whatever we got over there. Right. There we got 249.333 kg. Right. So the same amount we have got over here. Right. So that's the thing. So you don't need to worry about that. And then of course you can simply calculate the molar composition by you have the number of moles, so you can get the total moles and then the mole percent. All right. So I did it this way because I wanted to show you that both the ways it is possible. If you simply want to use the law of conservation of mass, then you can do that as well. All right. If you're using law of conservation of mass, then you can, and you have mass flow rates both the side or masses both the sides, then you can simply use outlet is equal to inlet, the overall material balance thing, right? So you can use that as well because for mass it is applicable, right? So once we are done with this, then we'll move on to example number 7. Please go ahead, pause the video and try to solve the problem yourself. Okay, so this is a very interesting question. See, methane and carbon dioxide react with each other to produce carbon monoxide and hydrogen. The product stream contains, they have given product stream composition. The product stream contains 100 kilomole carbon monoxide, 5 kilomole methane, and 12 kilomole of carbon dioxide. Calculate the percentage excess and percentage conversion. So let me first of all give you people the reaction stoichiometry. So we have methane and carbon dioxide. They react to give carbon monoxide and hydrogen. So when you balance the chemical reaction, it's going to be 2 CO and 2 hydrogen, right? So that's there. Now they have, let's draw the block diagram for this. So they have supplied methane and carbon dioxide and carbon dioxide. All right. So let's say they have supplied X kilomoles of methane and Y kilomoles of carbon dioxide. Okay. And we have got unreacted methane, unreacted carbon dioxide, carbon monoxide form, and hydrogen form. Right. So obviously, by stoichiometry, you can see that for every kilomole of carbon monoxide form, 1 kilomole of hydrogen is formed. So if there is 100 kilomole of carbon monoxide, then definitely by stoichiometry, there is also going to be 100 kilomoles of hydrogen. All right, that is very sure. All right. Then they have also given that 5 kilomole of methane and 12 kilomole of carbon dioxide. 5 kilomole methane and 12 kilomole carbon dioxide. All right. So now let's see how to solve this particular problem. All right. So first of all, we are going to write an equation for methane balance. All right. So methane balance is basically methane in minus methane out is equal to methane consumed. All right. And the next equation I'm going to write is for CO2 balance. And CO2 balance, the equation is going to be that CO2 in minus CO2 out is basically CO2 consumed. Right? CO2 in minus CO2 out is equal to CO2 consumed. Right? So based on that, we can get the two equations that we need. And one more equation that we can get by stoichiometry is that carbon monoxide or hydrogen, whatever. So whatever is formed is twice that of CO2 consumed, right? From stoichiometry, you can see that if, let's say, 1 kilomole of CO2 have reacted, then 2 kilomoles of CO will be formed. So CO formed, this is by stoichiometry, CO formed is 2 times CO2 consumed, which is again 2 times CH4 consumed, right? Same thing, right? CH4 consumed, CO2 consumed, same thing, right? So CO formed is 100 kilomole. So 100 kilomole is equal to 2 into CO2 consumed. And that is equal to 2 into methane consumed. So when you divide this entire equation by 2, both sides, all the 3 sides, so you'll get 50 is equal to CO2 consumed. CO2 consumed is nothing but Y minus 12. And that is equal to CH4 consumed, which is X minus 5. So from here, when you equate 50 and X minus 5, you will get X as 55. That is CH4, 55 kilomole. And then when you equate 50 and Y minus 12, you get Y equals to 62 kilomoles, which is CO2. So since both are in stoichiometric proportion, CH4 and CO2 has 2 in 1:1 ratio, therefore definitely CH4 is the limiting reagent, right? So CH4 is the limiting reagent. Okay. So since CH4 is the limiting reagent, therefore percentage conversion is equal to CO2 CH4 supplied, that is 55, minus CH4 left, that is 5, upon CH4 supplied, that is 55, into 100. So that is going to be 50 upon 55 into 100. So that is 90.91%. All right, 90.91%. That is your percentage conversion. Then percentage excess is basically CO2 supplied minus CO2 theoretically required upon CO2 theoretically required into 100. So for 55 kilomoles of CH4 supplied, you need 55 kilomoles of CO2. So therefore, the percentage excess that you're going to get is equal to 12.73%. That is your percentage excess, right?